So, hi, I'm Colin, and I'll be talking about seeding black holes into cosmological simulations and what we can learn from using different seed models from a post-processing analysis. So I'll give a brief overview of the simulation, but most of my work is all post-processing analysis, or most of this work is post-processing analysis. So the specifics of the simulation aren't as crucial. So then I'll get into, when you change the seed model, what does this tell us about when and where black holes form? What does that mean for populations of black holes that we can actually observe? What does it mean for the early growth of black holes, and also mergers between black holes? So, like I said, it's looking at cosmological simulations, so we're ranging from very large scales down to very small scales. The small scales use subgrid models, and that's where seeding is often problematic. So this analysis I'm using Illustris. So there was a bit of discussion just about Illustris TNG. Illustris was the first version. It's similar enough for the sake of what I'm discussing. So you've still got gas cooling, you have star formation, stellar feedback. It's a 75 H-inch megaparsec box that's run Redshift 0. So it gives us all the information we're going to need. I'll be talking about black holes, so just a quick overview of the black hole model in Elasticity. So black holes grow in one of two ways. There's gas accretion, which follows a Bondi-like formalism, and they also merge with each other. Obviously, their masses simply combine during that process. While the simulation is running, it self-consistently models black hole feedback, so there's a quasar mode and a radio mode, and also radiated feedback that's put in as well. The key point for what I'll be talking about is how we seed black holes. So in Illustris, as is the case with a lot of simulations, especially SPH simulations, the seeding is based solely on the mass of halos. So you run a friends of friends finder, and anytime you have a halo above a certain threshold mass, in our case 5 times 10 to the 10, if there isn't already a black hole in it, you just put one in. So it's not trying to model where black holes actually should form. It's just saying once the halo has grown to this size, we expect a black hole should have been formed at some point earlier and grown to be on the order of 10 to 5 solar masses. So it's placed in and trying to be consistent with whatever seeding models are currently being considered. So this kind of simulation has been tested a lot. So you've got quasar luminosity functions, which match pretty well with observations, and you have scaling relations, where again, we're able to reproduce observations quite well. So I said that this idea of seeding is supposed to be consistent with whichever seed model you're sort of considering. Here's just an example of some of those. So the seeds could be forming from population-free stellar remnants. At slightly higher mass scales, they might be coming from runaway interactions in dense nuclear star clusters. And typically at the highest mass scales, you can just have a direct collapse of a huge gas cloud into a very large black hole. So what I was interested in doing is trying to see what can we learn about how these different mechanisms actually embed a signal in observables that last throughout all the way down to Redshift 0, as well as what it implies for the early behavior of black holes. The problem with that is if you want to change how you seed black holes in a cosmological simulation, that's happening at the beginning, so then you have to run the whole simulation again. And every time you want to change the model, you have to run it again. These are very expensive. So instead, I'm just looking at this entirely as post-processing. So every time a black hole property is calculated in one of these simulations, the output saves all of the local gas properties. So at any given time step, I can recalculate what the accretion rate should be, which is Bondi-like, so it's depending on the gas density and temperature and the mass of the black hole. So what I can do is I can recalculate all that and also change properties. So here's an example. This is one black hole at redshift 0.5. And in black, you're seeing every single other black hole that merged with that black hole at some point over its history. So this is a single black hole merger tree, essentially. And in red, you can see the most massive progenitor history. On the right is what happens when I recalculate all of that using this method. So it looks essentially identical, which is good. It means what I'm calculating works out. It also isn't very useful because we already have all of that information. But we can also change properties. So we take all of those calculations and then we can say, well, what happens if we seed them at different times and then recalculate it? Or you seed them at different masses and then recalculate. So on the left is the exact same history I just showed you, just with a larger y-axis range. And on the right is the same thing, but I've now recalculated it where instead of the seed mass being 10 to the 5 solar masses, the seed mass of each black hole is selected from a Gaussian distribution between 10 to the 3 and 10 to the 5. And the red curve here is the original illustrious run, most massive progenitor, and the black is from the recalculation. So you can see the final mass is almost an order of magnitude lower, just by changing the original mass of the seeds as the black holes form. Here, all these colored lines are now showing you a dozen different realizations where I've selected different random samplings of possible seed masses. So you can see they do converge onto one value there, which is well below. But you can also see what you care about is higher redshift. You're getting a very wide range of possible behaviors. So how you're seeding it can have a very important impact on high redshift behavior. And also you can see it's going to have an effect on low redshift because by the end of the simulation, all these alternately seeded models are almost an order of magnitude less massive. So I've taken that approach and applied several different seeding models to the entire illustrious simulation. So one of them is I just assign every black hole a probability to be seeded. So f seed of 1 is just going to reproduce illustrious. F seed of 0.5 means only half the black holes in illustrious would ever form. Another possibility is where we seed based on the spin of the gas in the galaxy. So if it's too high of a spin, then we're assuming it's not going to be able to collapse into a direct collapse black hole. And so here you can see a sample. This is all of the galaxies in illustrious that form black holes in the original redshift versus the log of the spin. So you can just assign some value and say we'll only seed anything below that threshold. And if you want, you can do the same thing with metallicity. So we've done something similar. So if we do that, here's an example of the fraction, the blue, green, and red lines. This is the fraction of black holes from illustrious that get seeded as a function of redshift for several different cuts on gas spin. And so you can select them, and it's relatively redshift independent. If you're depending only on gas spin, they're going to just get seeded pretty much equivalently to what illustrious originally did. What gets more interesting is if you try and apply a much more physically meaningful, physically motivated process. So in this case, what we do is we look at for every galaxy, we look at its entire progenitor galaxy history. And for every one of those progenitor galaxies, we check to see if they ever satisfied all three of these criteria. So we require that it be massive enough that we can form a massive seed. We require that there be low metallicity, essentially very pristine metallicity, so that you're able to collapse without fragmenting and form a massive seed. And you also require the gas spin is low enough that it won't be rotationally supported. So this is an example of just one galaxy that we check. So every single dot here is a different galaxy progenitor, and we check all of these criteria. And in this case, one of those progenitors at one point in time satisfied what's necessary. So that galaxy would form a black hole seed. So if we look at this, the cumulative fraction of galaxies which satisfy this, you can see it's typically on the order of 10 to 20%. So only about 10 to 20% of galaxies in simulation have progenitors that ever satisfy these criteria. So we're going to be seeding a lot fewer black holes than the original run did. So then we can take a look, once we apply all of that, what does that mean for the observables? So here we can see, this is the quasar luminosity function, redshift 4 and 2. And the different colors represent different fixed probabilities of black holes being seeded. So you can see, obviously, the more rare it is to seed a black hole, the lower your luminosity function is, which is not surprising. But it's still quite consistent with observations. In pink now, that's put on top our full progenitor-based seeding model. And so you can see, at the bright end, it's very consistent with what we observe. At the faint end, you do start to lose some of these low luminosity objects. If you go to lower redshift, and this is now redshift 1 and 0.5, you can see the fixed seed fractions all converge, and you have no way to distinguish between them at low redshift. And the same for our full model at the bright end, but at the faint end, you are able to have some distinct behavior because you're losing out on the very low luminosity objects. So we can also look at the black hole mass function. So this is essentially the same plot as we just saw, except instead of luminosity, it's now the mass function. That gives us a little bit better sense of what's physically happening. And so you can see at all redshift from 5 to 1, there's a nice discrepancy between these different seeding models. And you put our full progenitor model in, and at high redshift, it's very consistent with just seeding at approximately 25% of all galaxies. When you get down to low redshift, though, you start to lose the very low mass objects. And that's because the only things that are being seeded are at high redshift. At low redshift, we're not seeding black holes much anymore because the typical metallicity of the gas is too high. And so our progenitor model no longer gets satisfied at any point. However, I want to point out, here's the luminosity function at redshift 0.5, and here's the mass function. And if you look, the luminosity function is completely converged for all of these different models, whereas the mass function is not. So what's happening here is we have the black holes are different masses than in the original run, but typically the same luminosity. And that's basically because in the cases where the black holes are able to grow more efficiently, they reach a self-regulated regime sooner, and so then their luminosity doesn't continue increasing because they start being self-regulated. The ones that grow less efficiently to a lower mass are actually growing more efficiently in terms of their Eddington fraction at the end of the simulation because they are not yet self-regulated. So it's lower mass, but higher accretion efficiency. So you can explicitly see this. These curves are distributions of Eddington fraction. So on the right at redshift 1, you can see whichever model we use, they're pretty much all the same. And higher redshifts, they're even more similar to each other. Once you get down to redshift 0.5, you can see the less efficiently you seed these black holes, typically they're lower masses, but they accrete much more efficiently. And if you consider our full model, which is based on the galaxy progenitors, that's the most extreme case of all. And you typically have a much higher average Eddington fraction. So that's telling us a lot of what happens in the end, but we can also consider what happens at the very beginning of these black holes' growth period. So here we're looking at the redshift at which Illustris actually seeded a black hole in the original run. And on the y-axis, that's the redshift at which our model says it really should have formed. So you can see most of the black holes in Illustris actually form between redshift 2 to 3, 2 to 4. But according to our model, those same objects should really have formed close to redshift 7 and have had quite a bit of time to grow as you're pushing down towards low redshift. So given that, we can make some predictions on what must be happening at the very early growth periods. So this is a distribution of seeds above redshift 5 comparing how much before Illustris put the seed in it should really have formed. So on average, Illustris is putting in redshift 5 and above seeds about 500 mega years after the seed should really have formed. So that black hole then has about 500 mega years to grow to reach the seed mass that Illustris has put in. So we can actually convert that from typical time to what it means about the mass of the real seed that formed and the Eddington ratio at which it's been growing over those approximately 500 mega years. So this is for a variety of different seed masses. But you can see in green, for example, that's if you assume that these seeds form at 10 to the 4 solar masses. In that case, you can see on average, they're still growing well below Eddington to be able to match what Illustris originally had. So we can push down, you can see you can even go down to 10 to 3 in pink. And while some of them would have to grow super Eddington, most of them can still grow at sub Eddington and still match a 10 to the 5 seed that you put in later. So this is suggesting that in fact these direct collapse black holes could be forming at much lower masses. It doesn't have to form at 10 to the 5. It could be forming at 10 to the 4, 10 to the 3, and still not have any long-term differences from what a lot of these simulations tend to deal with. So the last thing I'll discuss is mergers. So obviously the more often you're seeding black holes, the more mergers you will have. So when we change how we seed these black holes, we're going to end up decreasing the rate at which we should be observing black hole mergers. And with potential upcoming surveys like ELISA, which should actually detect gravitational waves from supermassive black hole mergers, giving some estimates on what rate we expect these mergers to happen as a function of how the seeds actually form is rather significant. So here I've shown you, every little position here is just showing you the number density of mergers in the entire history of the universe from the simulation as a function of the mass of the two different black holes. So the more massive and the less massive black holes involved in the merger. So the three panels shown here are just different rates of seeding. And so you can see, obviously, if you seed 10 times as often, it's much more often that you'll get mergers occurring. But the actual distribution as a function of the masses involved doesn't change. So, and from gravitational waves, we should be able to tell how often these things are being seeded, but only if we can really nail down the rate at which they're actually merging in the real universe, and not from the distribution of the mass ratios involved in the mergers. However, if you include the full model I've been describing, where you're really considering how the progenitor galaxies behave, then you get a different behavior. So this is now the black hole merger rate according to our full progenitor-based seeding model. And so you can see, instead of being focused around a bit of a lower mass and continuing all the way to very massive single black hole with a very low mass secondary black hole, we tend to be focused much more on major mergers where the masses of two different black holes are fairly comparable. And generally around 10 to 7, 10 to 8 is the peak that occurs. So that tells us that just from the shape of the mass ratios of mergers that get observed, we can actually distinguish between some of these different seeding models. Even if we aren't sure if we're catching all of the mergers, as long as we have a reasonable understanding of the distribution mass ratios, we can start distinguishing between these. So, just to summarize, without having to rerun simulations, we can change seeding models and see what that implies for both high redshift and low redshift quasar populations and AGN populations. We can also see what we expect to happen in the very early growth between when the real seed forms and when most cosmological simulations start to include that. And so we can see what that does for luminosity functions and mass functions, what it does for the distribution of Eddington ratios, and for the rate of black hole mergers. And then there's a lot more that this kind of modeling can include, so we're also continuing to add more criteria, like including Lyman-Warner radiation before these things can be seeded, and incorporating population 3, stellar mass, stellar remnant seeds, and nuclear star cluster seeds. But so far the results are very promising. Thank you.